Let's go from current slide. The only announcement I know about, well, no, there's two. First, has everyone done the student course evaluations? Not yet. Oh, some have. Excellent. Okay, excellent. You have until August the 8th, but I would not wait until August the 8th, because by that time you've turned off the Etch-a-Sketch, shaken it, the screen's clean. Go on and get them done while you're thinking of it. If you want to wait till you see that grade, fine, but get them done shortly thereafter. Okay. Now, the other thing is, goodness gracious, they pile all this stuff in at the end of the term, and it's just really ridiculous. But we have tomorrow a planning hearing at 1:30 over on the Birmingham West Campus. So that means my office hours tomorrow will be nothing like what's posted. I'll be available from 10:45 up until close to 1 o'clock. Before 1, I've got to leave to go to the Birmingham West Campus. I may have to actually leave sooner if some people have more documentation they brought in by tomorrow morning, because I've got to get it in the binder. So I may actually be gone well before 1 o'clock. So anyway, there's that. After that's over with, then hopefully I'll be able to get back on a regular schedule. Hopefully on Thursday I'll be 10:45 to close to 4 o'clock. Probably I'll start leaving about 3:45, because it's been harder and harder to get over there in half an hour, trains and other things. So anyway, we'll try to get this final thing, but it's right at the end of the term now, and it's nuts. And I've still got some stuff to do with fall schedule to clean up. And I'll my glasses again. Here's Teresa. All right. We've got enough for a basketball team. All right. Okay. Now, any questions before we get started? We go and turn on the projector. Should have had that on while I was doing the announcements. And as soon as it comes up, we'll get going. Any questions so far? All right. We're in Chapter 4, Integration. 4.4 is Fundamental Theorem of Calculus. Actually, the way this book does it is Fundamental Theorems of Calculus, meaning both 1 and 2, first and second. Other books call it one theorem, and they say Part 1 and Part 2. But however you name them, that's what we're dealing with now. And we're basically doing application of that in what we call the net change theorem. Okay? Now, fundamental theorem of calculus states that if f, some function, is continuous on a closed interval a to b, and capital F is the antiderivative of f, little f, on a to b, then the integral from a to b of f of x dx, the little f, is equal to antiderivative evaluated first at b and then subtract the evaluation at a. Fundamental theorem of calculus, Part 1, or this book is called the Fundamental Theorem of Calculus. But because f prime, capital F prime, is little f, this statement can be rewritten as the integral from a to b of, instead of little f, put capital F prime of x dx, and that's equal to capital F of b minus capital F of a. Or the quantity this represents the net change of f, capital F, on the interval a to b. This is the net change that f endures or goes through on that interval. Okay? Which, that's what a subtraction is, a change, difference. Okay? Now, that leads into this theorem. If f prime is the rate of change of a quantity, capital F, then the definite integral, capital F prime, from a to b gives the total change, or the net change. Okay, those words sound different, but they mean the same in this context, of f on the interval. So remember, f prime is the rate of change. That's what a derivative is. How f changes per unit x. Okay? And capital F would then be the total. The difference between the capital F is the total change, or they call the net change of F on that interval A to B. Okay. Nothing new here, just another restatement and a kind of another way of looking at integration. Okay? Any questions? Here's example 9. Okay? A chemical flows into a storage tank at a rate. Now, folks, get used to this. When you see a rate, think derivative. That's what a rate is, a derivative. A rate of 180 plus 3t liters per minute. Okay? So what is this the rate of? Liters measures volume, so this would be dV dt. That's the rate you're looking at right there. Units are your friends. They help you see what's going on. Where t is the time in minutes, and that's going from 0 to 60. That is your interval that we're dealing with right here. Find the amount of the chemical that flows into the tank during the first 20 minutes. So we're not doing the whole interval, we're only doing the first 20 minutes, from 0 to 20. Okay? So a chemical flows into a storage tank at a rate of that. Rate meaning dV dt, okay, where V is in liters, T is in time, minutes. T is time in minutes. And let's do it. That is our dV dt, so that is what's inside the integral, okay? What we were calling capital F, we're now calling capital V, okay? So let me get my pen set up. Okay? So this tells us D, now if you want to call it something else other than V, that's fine. If you want to go back to capital F, that's fine. I don't care what you call it, but just realize, whatever that is, I'm just choosing V because I think of liters as being a volume. dV dt is equal to 180 plus 3t. Okay? Or you could call that V prime. Or you could call it F prime. I don't care what you call it. Okay? Now, find the amount of chemical. The total amount would be the integral. The sum of all that. Total amount, sum of all that. So this would be V as a function of t is equal to the integral from 0 to 20, because the t is in minutes, so your dt is in minutes, so that's what your t is going from, and this will be 180 plus 3t dt, and it's pretty simple to go from there. What would be the result of that integration? Antiderivative of 180 dt, 180 t, second, plus 3 t squared over 2, evaluated from 0 to 20. Okay? Do it. What's the evaluation? Okay. If you're evaluating that on 20 times that, easy way to do it, just put down the 2 zeros, one from the 20 and one from the 180, and then double your 18. That's 36. Okay. Plus, all right, 20 squared is 400. Half of 400 is 200 times 6 would be, times 3 would be 600. So this would be 4,200 liters. Okay, units are your friend. That's your liters. That's why I said volume in liters. Let's see how they did it. Oh my goodness, look at that. So the amount of chemical that flows into the tank during the first 20 minutes is 4,200 liters. Okay? Make sense? Okay, keep it there. Okay. Making sense so far? Any questions? All right. Let's see how they did it. Let's erase my scratch, and we'll see how they did. Let's see. I don't know why they choose C. Oh, amount of chemical. Okay, I guess so. C of T. Chemical in the tank, C of T. Chemical in the tank, amount of chemical in the tank at time T. Just as good a variable as any. You can name it anything you want to. Okay, then C prime of T is the rate at which the chemical flows into the tank. dC dt, the rate, amount of chemical flowing per minute. Okay, which is what they told us there. So during the first 20 minutes, the amount that flows in the tank is 0 to 20. C prime of T, dt, this is the rate at which it's flowing, times the amount of time that it's flowing, and that would be, this is rate per unit time times time, that will give, the amount per unit time times time, that will give you a total amount. That's what an integral is. It's a summation. Okay, 0 to 20 of 180 plus 3t dt. Do the antiderivative, 180t plus 3t squared over 2, or 3 halves t squared, however you want to do it. Evaluate from 0 to 20, just like we did. 3,600 minus plus 600 is 4,200, and that will be liters. So the amount of chemical that flows into the tank during the first 20 minutes is 4,200 liters. All right. Now, is this even a, and this is important, it's just a sort of a dumb question, but is this even, to me this problem really doesn't make a whole lot of sense, because this is saying at time t equals 0, you just got 180 liters per minute flowing into the tank, but then for every minute after that, the rate is increasing. So I see no reason for that to be happening, but that's what the problem says is happening. So you do what the problem says. But by 60 minutes, boy, it would be flowing in there very, very, very rapidly. In fact, twice as fast as it did at the very beginning, because 60 times 3 is 180. So it's just sort of a made-up problem, but to me it's not a very realistic problem. Sorry to dash that. Okay? Any questions on that? They don't have to make sense, just do them. Okay. Just sort of kidding. Another way to illustrate the net change theorem is to examine the velocity. Oh, I didn't ask. Does anyone need that up any longer? It was what we had already done. Is to examine the velocity of a particle moving along a straight line, where s of t is the position at any time t. So if right here at time t equals 0, the particle here, and t equal 1, it'll be there, and t equal 2, it'll be there. T equal 3, it actually went backwards and went there, and then t equal 4 went there, and, whatever it's doing, this is the position at time t moving along a straight line. Then the velocity, v of t, which is the derivative of s, the rate of change of your position at any time t, would be the integral of this. This is rate of change of position. This would be your position at time b minus position at time a, because its v of t is s prime of t. That definite integral represents the net change of position, or also called the displacement of the particle, the total displacement of the particle. Okay? So if it did start here, okay, now, I just said total displacement. You have to sort of take that with a grain of salt. This is its position, not total displacement. It is a displacement, but not total. Because if it started here like I described, it went here, and then went here, but then backed up here, and then went again here, this would just be the change from here to there. That's all. That's the change of displacement. It wouldn't be the total displacement in a sense, because you see it went here, then backed up and went back here. This part would not be counted twice, only once. Okay? Because it went there. So this is and this is one reason they call it net change, the net displacement of the particle. Now, that's sort of a little picky point, but it is sometimes useful to consider. When calculating the total distance traveled by the particle, okay, you must consider the intervals on where the v of t is less than 0 and the intervals where it's greater than 0. That's what I was just talking about. The total distance traveled, he would have traveled this distance, then that distance, and then that distance. So you see, that's a greater distance than the displacement at the end. Okay? When v of t is less than 0, the particle moves to the left, and when it's greater than 0, it's moving to the right. That's the convention. To calculate the total distance, you integrate the absolute value of the velocity, keeping the velocity constant. Now, does anyone know another name for absolute value of velocity?
Speed.
Speed, exactly. That's the speed of the particle. Doesn't matter which direction it's going, that's the speed. So you can think of that in that context. So the displacement of the particle in the interval a to b is simply the integral from a to b of your velocity, no matter what direction it's going, and that will be, goodness gracious. Okay, they're referring to this down here, and but they had it up here. I thought, what? Where did this come from? Okay. See here, the velocity is positive. Okay, velocity positive. So therefore, it's displacing and started off going slowly, then pick up speed and displacing more and more. So the area under here is the total displacement. Okay, got here, and then right here, the velocity comes to 0. See the velocity decreasing here until it stops. Right there, it stopped instantaneously. It started backing up because velocity is negative now. Okay, so the displacement of it went forward this much, and then went backward that much, and then went forward again. So this is this area minus this area plus that area, because it went back and then forward again. The total distance traveled is the absolute value, so you take the A1, just like we saw, and then the absolute value. You flip this over, because absolute value makes it positive, plus A2, this area under here, plus A3. Okay? That's going to be a larger distance traveled, because you count the distance here and there. You know, you count all the distance that you move, whichever direction it's going. Okay. So the velocity in feet per second of a particle moving along a line is this, where t is the time in seconds. Says what is the displacement of the particle on the time interval 1 to 5. Okay? That's pretty easy, I think, I hope. What would that be? And for some reason my screen is blanking out every now and then. So what would be the displacement of the particle? Anybody? The displacement of the particle is just simply the antiderivative, or the integral of, the definite integral of the velocity over the time period, right? There at the top, okay? So what would it be here? What is the displacement? That's going to be S of t is equal to what? I'm sorry? I can't hear you. Okay, the total displacement will be S. This is your S prime of t. So that's what you integrate here to get the S on the outside, right? Yeah, antiderivative of this thing up here. And what would that be? And this will be going from 0 to 5 of t cubed minus 10t squared plus 29t, I've got to sneeze, sorry, minus 20. Y'all awake yet? Okay, good. Okay, dt, and what would that be? And you started doing it earlier. What was that? T to the fourth over 4 minus 10t cubed over 3, 29t squared over 2, 20t. Evaluated from 1 to 5. What's that? Not with definite integrals. I misstated down here. I thought it was 1 to 5, 0 to 5. It's 1 to 5. No, when you do a definite integral, you don't need the plus c. Indefinite integral, you do need the plus c. Okay. That was one of the real big advantages of fundamental theorem of calculus. You don't need the plus c's anymore. All right. So, when t is equal to 5, what is 5 to the 4th power? Anyone know? What's 5 squared? 25. What's 25 squared? Anyone know? 625. Because 25 or 5 cubed is 125, and then another 5 times 625. 625 over 4 minus, right. All right. Is anyone else coming in? We lost one, gained one, but I think the one's coming back. Okay. We're on example 10. We're in chapter 4, integration, 4.4, fundamental theorem of calculus, page 291, and this is example 10 on 291. We've just done the integration. We are now evaluating it. So minus 10, and what was 5 cubed? I just said it a few minutes ago. 125, perfect, and that's divided by 3, plus 29 times what's 5 squared? 25 over 2 minus 100, okay? 20 times 5. But now we have to subtract, okay? So subtract when we put in a 1 there, okay? So this will be, when t is 1, this will be t to the 4th. 1 to the 4th is 1 to the 4th is 1, so that's 1/4, but it's a minus because we're subtracting the bottom one, okay? But then we got a minus the minus, so that's going to be a plus. Now, how in the world did I get 100 up there? That's a 10. Someone is out to lunch and not paying attention. Say that again? Yeah. Okay. Malcolm Jack came in just in time. Okay. All right. All right. So minus a minus would be plus 10 times 1 cubed is? What? 1. So that minus 1/10. Okay. Then we got minus a plus, which will be a minus 29 times 1 is 29 halves. And then a plus, what? That last 20. Okay. Now, a little bit of algebra, or actually just simple math. 625 minus 1/4 is 624. I think 4 will go into 624. I know it'll go in sometimes, but will it be an exact number of times? 4 will go into 6 1 times with 2 left over. 4 will go into 22 5 times, and to 24 6 times. So I think that turns out a 156, right? Got what I was doing? Okay, good. Okay, the next one is, this, by the way, is 1250 thirds minus 10 thirds. That would be a 1240. Let's write it on out. Plus 1240 thirds. And that will not work out evenly. Sorry about that. Okay? But that's a minus, sorry. It's a minus. All right, the next one will be, oh boy, 29. Is there some easier way to do this? 29 times 25 halves minus 29 times 1 half. That'll be 29 times 24 halves, so that'll be 29 times 12, I think. I'm sort of doing it in my head, and then we finally got a minus 80. Okay, now I don't know, you could have done it with your calculators, I just didn't have a calculator, so someone will punch those numbers in and tell me what you get. 156 minus 1240 divided by 3 plus 29 times 12 minus 80. And see what you get, the displacement of the particle. And this should be in feet. Anyone got it? Anybody got it?
10.66.
Say again.
10.667.
10.667. Okay. That would be feet. Sure doesn't look like it went very far, did it? Why? Because some of the time it was going backwards, and some of the time it was going forward, and then backward again and forward again. Now, what's the total distance traveled by the particle on that time interval? Okay. Now, this is a little bit harder to deal with because you have to take into account the, let's see, they got 10, they left as 32 thirds, which is the answer you got. And that would feet to the right because it's a positive number. But what's the total distance traveled by the particle on the time interval? 1 less than t less than 5, okay? Between 1 and 5. Here you almost have to draw the graph of that velocity function and see when it's positive and when it's negative and break it into two pieces. And that's a pain in the neck somewhat, okay? So the best thing to do is to take this thing and set it equal to 0. Because obviously, well no, it's not obvious, but at time t equals 0, the velocity is negative, which is interesting. Oh, yeah, but we're not doing t equals 0. We're doing t equal 1. Okay, sorry, did that again. When t is equal to 1, then you've got 1 minus 10, that's minus 9, plus 29, so that would be plus 20 minus 20. So yeah, you got a positive velocity there, so you are going forward at time t equal 1. Okay, so we will start there, and let's find our zeros. We know at time t equal 1 is positive. Now, it's going to be positive until it reaches a 0, because that's a continuous function, and then it'll go negative. So the first thing we're going to do is take this thing, 10 cubed minus 10, t cubed minus 10t squared plus 29t minus 20, and set it equal to 0. And see where we have a direction change. Because when we start off, when you put a t equal 1 in there, we just did it, we found out we were going at a positive 9, I believe it was, feet per second. So it's going forward to at time t equals 0. Let's see when it goes otherwise. Okay? Now, that's not a particularly easy thing. Okay. Can any of you factor that right off the top? I can't. If you can, more power to you. Okay? Now, I don't know if you remember back from pre-calculus algebra, some of you had better because you were in my class, how we find those zeros. Okay? First thing, we've already tested t equal 1. It doesn't work. Okay? So what we do then is use your rational zeros test. Anyone remember how that goes? It's all the possible factors of your constant term, which would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus, oh, so not 3. 3 won't go into 20. Sorry. This will only give you rational zeros, okay? Plus or minus 2, plus or minus 4, plus or minus 5. 6 won't go into 20, 7 won't go into 20, 8 won't go into 20, 9 won't go into 20, but 10 will, plus or minus 10. And that's all, folks. Okay? Right? Oh, and plus or minus 20. Okay. So those are your and that's all over your constant term, which is plus or minus 1. I mean, your leading term, plus or minus 1. Well, that doesn't contribute a thing. Okay? Now, we've already tested 1, and it doesn't work. Okay? We just plugged in 1 and saw it was a positive number. So let's get the next one, 2. Okay? Now, there we probably do a synthetic division. Okay? So let's do synthetic division. 2 on the outside, and you have 1 minus 10, 29, and minus 20 on the inside. Now, count the number of terms, 4 terms. Your maximum exponent's 3. That works. Skip a line, draw a line, and do a 1. Okay? Now, I'm going to do another timeout, but I'll wait just a minute. Bring down the 1, okay, and then multiply. 2 times 1 is 2. Minus 10 plus 2 is minus 8. 2 times minus 8 is minus 16. Minus 16 plus 29 is 13. And that would be a plus 26. Not 0. So 2 will not be your turning point. Okay? So 2 won't work. And by the way, it's still positive. So because you had a 6 remainder. So we've still got a positive there. So let's do the next one. Now this only works for rational zeros. If this comes out being an irrational number, you're not going to find it this way. But at least it gives you somewhere to start. The next one would be 4. All right. Time out a moment here. This is what I meant to say earlier. Are we really interested in negative time? No. Okay, we're only interested in positive time. So those plus or minuses there really don't matter. We're only looking at the pluses. That's why I didn't even bother with minus 1. That's why I'm not bothering with minus 2. We're only looking for positive time. Times between 1 and 5. Okay? 2 is between that. 4 is between it. Shoot, if we don't get 4, we're sunk. So let's hope 4 works. So let's see if it does. 4 times 1 is 4. Next. Negative 6. Negative 24. 5. 20. Ding, 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 ding. We have a winner. Okay, a winner. Okay? We found the next 0. Okay, that means at time t equal 4, your velocity is 0. Okay? Now, we're hoping it didn't, it was a positive velocity at t equal 1, and we're hoping It didn't dip down at some irrational number and come back up and then hit 0 coming up. We're hoping this is just going to be at t equals 4. You could try by evaluating some number close to 4, like 3.9, and seeing if that comes out positive. But for right now, we're just going to say, let's just hope that stays positive the entire time up till then. Okay? So at time t equals 0, it goes to 0. I mean, t equals 4, it goes to 0. And then we just are going to assume it goes negative, because that's a single 0. What we have left here is t squared minus 6t plus 5. That's what your quotient is. And if you were to do that, that would be t minus 5 times t minus 1. Well, this is your quotient, right? We got that by taking out the t's when we were doing our synthetic division. We put them back in now, but we reduce it by 1, as we did in pre-calculus algebra, remember? Okay? So, and then we factored that, and that was so surprising because that gives t equal 1 as being a 0, and we just found out it wasn't a 0. So that's sort of a big bummer to me. But t equal 5, it's going to be 0 again, so we're not going to worry about that. Did I do that right? T equal 1. Okay. T1, oh yeah, you're right. It was a 0. Yeah. So the velocity was 0 at time t equal 1. I don't know how I missed that, because it was 30 minus 30 is 0. So it started off at 0, and we don't know, but it did go positive after that. It went 0 at 4, and then went 0 again at 5. Okay? So that is what it tells us. Now, we didn't find out for certain that it was positive there, but you could just plug in t equal 2 and find out, sure enough, that's positive. But my plugging in has not done well so far. But yeah, so we have positive velocity for the first 4 seconds, negative for the next second. So then the total distance traveled in that time period would be, and what do they give as that? They don't say what it is. I'm going to still call it S of t, but this is total distance, not displacement. Okay, not a displacement, but a distance. And that came out looking really ugly. This S is distance, not displacement. This S was displacement. Okay. So this is going to be the integral from 1 to 4 of t cubed minus 10 t squared plus 29t minus 20 dt. Okay. All right. And then we've got to do the absolute value of this, which then, because we know the velocity here is negative, we do a minus the integral from 4 to 5 of t cubed minus 10 t squared plus 29 t minus 20, okay, dt. Now, why that? Because we know the velocity is negative between 4 and 5, so we're doing the absolute value of this would be the negative of that value. Because we know it's negative there, so we do the negative of it, so that's what pulls the minus sign out here.
So what we did the factor and stuff, what we do already?
I'm sorry?
Just figure out that it's negative between 4 and 5.
Okay, I couldn't hear any of that, so I hope, does that answer the question that I couldn't hear? Okay. Yeah, because the first one is the displacement. How far was it? You know, you started here, and for the first 4 seconds you went this direction, then the next second you came here, the displacement is the difference between here and here. Not how far you totally went, but here. This one down here, total distance traveled, would be this distance plus this distance. Even though that was a negative distance, we're doing the absolute value of that, so we would take this part and move it over here, and that's why you, second?
That's why you put negative.
That's why you put the negative sign, because you're going backwards. A negative of that will be, make it positive. Exactly. Okay. Now, the integration is exactly the same. It's just the evaluation of it. So this will be, and it's the same as we did before, so there's nothing new here, except that we have different values. Now, can I go up and use that to keep from rewriting everything? Okay, we're going to whoa, I think I just messed something up. Okay. All right. Okay. Here is our integration. So here we're going to plug in. Okay. But this time we're doing, okay, let me get that corrected too. We're doing 1 to 4. Okay. So when you put a 4 in the top, anyone know what 4 to the 4th power is?
81.
Now 3 to the 4th power is 81. 4 to the 4th power is 4 squared is 16. Say again? 256. Perfect. So that would be 256 over 4. Okay. Which, since you're dividing by 4, we could have made that a little bit simpler here and just made it at 64. Okay. So that's 64. And actually, right. Does anyone else come in just to call roll? I haven't really been paying close attention. Hope we got everybody now. 2, 4, 6, 8. 2, 4, 6. Got it. Okay. All right. 64 minus 10 times 4 cubed is another 64, right? But this time over 3 plus 29 times 16 over 2, which I'm just going to make that 8, okay, minus 20 times 4 is 80, okay? And then the minus 1 is exactly what we had down there. Minus 1/4 plus 10/3 minus 29 halves and plus 20. Okay. So we'll come back and do that in a moment. Okay. Now let's do the next part here. I'm going to erase my synthetic division here because we've already used that. We got what we need from it. Don't need that anymore. Now, same integration, okay? Only we've got a minus in front of it now, okay? And that's going to be 10/4 over 3, evaluated at 5. We already did that before. I wish I hadn't erased it now. Why did y'all let me erase it?
That's all right, we wrote it.
You wrote it, okay. So that would be 625, wasn't it?
Yep.
625 over 4. We're going to change signs, though, okay? Plus, because you see we got the minus sign in front, plus 10 times 125 over 3 minus 29 times 25 over 2, right? Yes. And then plus 100, wasn't it? It's exactly the opposite of what I erased up above. Sorry about that. Okay? And now we're going to do minus a minus, which is a plus, evaluated at 4, which is exactly this line again, right? It was a plus 4 here and a minus 4 here, so we get this one again. So let's just do this one times 2, okay? I know I'm being really obnoxious about this because I don't have much room to write. So if we do this, I think it'll work, okay? So let's do 2 times 64, that's 128, minus 2 times, what's that, 640, so that would be 1280 divided by 3, plus 16 times 29, minus 160, minus 1/4, plus 10/3, minus 29 halves, plus 20, minus 625 over 4, plus 1250 over 3, minus, I think that's a 29, no, yeah, 29, it's an ugly 9, 29 times 25 over 2, plus 100. See what we get. Anyone punch those numbers in? Or you have no clue what I was doing? Huh? Okay. All right, Jalen's here. Jalen will help us out. Thanks for coming in. Okay. All right. We're in Chapter 4, Integration, 4.4, Fundamental Theorem of Calculus. We're on page 291, Example 10. I know it's sort of a mess.
Hey, can we go back for a second?
Okay.
A.
This part?
Yeah. So, what you did, you took 5.
Right.
5. Okay, 5. And you plugged it into what we just got. You know,
Yeah.
625 divided
Yeah,
by
this
4.
is it right here.
Yeah. You subtracted that by the 1?
Yes, when you plug 1 in.
All right, cool. Just
And that was this line right here.
cool. Okay.
Okay? Now, what we're doing down here,
Including that 4 and then subtracting by the 1 on that side.
yeah, we're doing the 4 up here, which is what we wrote here, minus the 1 here, which is exactly like we had before. But then we do the minus 5, which I had to write down again, but thankfully you had written it down. And there was that line, but it's a minus this time. Then minus a minus, which is a plus 4, which was the same thing this was, so we just doubled it up here. Okay? So it's this one doubled, minus, plus this one with the sign changes, and then with the sign changes here, that gives you.
Why did you double it?
Because, okay, the first time we did it, it was 4 times all this because of here, right? I mean, not 4 times it, 4 plugged in there. And that gave us this thing right here. We did that with 4 plugged in, right? Okay. Then we did the minus 1, which is that one. Then we did the minus 5, which is this one. And then we did a minus 4, which was this one again. Minus a minus is plus.
I didn't know that.
Yeah. But you see?
Did you explain that?
Yes. So it's magic is the answer. It's just magic. This is where it came from. So that's why I doubled. All right. Now,
11.833.
that sounds reasonable. Is that the same as 71/6? I mean, it's okay.
Yes.
Okay. That's what they got in the book, is 71/6 feet, which is not a very comfortable. So what did you say your answer was?
11.8.
11.8 blah, blah, blah feet. Whereas this one up here was 10.67 or 10.7 feet, which they called 32/3, which is exactly what it was. Okay. All right. Now, if you want to see it a little more organized and straightforward, let's do how they did it. Okay? By definition, you know that displacement is just the integral of the velocity. Takes into account positive velocities, negative velocities. It's just where you started minus where you began, or where you ended minus where you started. And that would be going out here, coming back. It doesn't matter where you did. That's just your total displacement. So that's going 1 to 5 with that velocity, not mattering what the signs are, whether it's going forward or backward or anything else. You just do that. And that's the very thing we did. This is 10 to the 4th minus 10 cubed over 3 plus 29 t squared over 2 minus 20t. Okay? I may have said some of that wrong. Evaluated from 1 to 5. Okay? And you put those values in, and they don't show how they did it. They got 29 twelfths plus a 103 twelfths. Okay? If I'm just assuming this is what they did. They took least common denominator here of 12, okay, and then they did whatever that was, 625 minus 10 times 125 plus 29 times 25 plus 100. Hopefully that came out 25, and then they subtracted when it was a 1, and that was minus 1/4 plus 10/3, and again, the least common denominator is 12, minus 29 halves, minus 20. Hopefully that gave you that, the minus and minus make it plus, and they claimed that came up 128 twelfths, which reduced to 32 thirds. Okay. Not quite how I did it, but got the same answer. Okay? Now, that's your displacement. That was the A part. You need it up there a little longer. It's the same thing we did, they just did it a bit differently. They first evaluated all this at 5 and got this, evaluated all of that at 1 and got minus that, and then they went through their fractions. We did a little, I thought a little easier, evaluated this, subtracted off this, and saw what you came out with. Okay. Got it? Now, anyone need this up a little longer?
Can you go back to this one?
Second?
Is there any way you can go back to this one?
My slide? You really want to see that? Okay. Okay. Now this doesn't show the A part exactly.
Oh, no, I already got that.
Oh, yeah. All right.
Come on.
Okay. What we came up with, and Patrick plugged it in and got 10.667, which I looked at it, so yeah, the same as 32 thirds, which is what they got for theirs.
That's A.
Huh?
That's A.
Okay.
That's A, right?
That's the A part, right?
Yeah, I'm on B.
Yeah, and then the B part is down here. We haven't shown B part on theirs yet.
Oh.
Yeah, see, this is all their A. That's their A part. It's all A. Now we're ready to do B. Right? You want to see it? Okay, here's the B part. Find the total distance. They drew the graph and showed that sure enough, and if you have a graphic calculator, it's a great way to go. You saw from 0 to 4, from 1 to 4, it was all a positive velocity, so you do that one first. Then you subtract off the distance you went backwards. Well, wait. Subtract it off, but in other words, you added the distance you went back rather than subtracting the distance you went back. Okay? It can be factored into t minus 1 times t minus 4 times t minus 5, which we did. They did it based on the graph. We did it by synthetic division. We found that there's a 0 there, a 0 there, and a 0 there. Okay? Their graph showed there weren't any in between there. So you're all positive here, so you just do this integral from 1 to 4. You just do it without the absolute value bars. And then from 4 to 5, you do the opposite of it because it's negative. Okay? And that's where they do this. So the integral of the absolute value of this, do the part where it's positive, just evaluate that, integrate that from 1 to 4 of VOT, but then, just like we did, subtract off, because it's negative, the distance that you traveled from 4 to 5. And that gave you that. Now, the V's are the same. So the integration is exactly the same. Okay? This integrates just like it did before, just like this is going to do now. The difference is the signs. Okay? So this will be the same integration we had before, but now we're going from 1 to 4, not 1 to 5. Okay? Minus, though, the same integration this time from 4 to 5. Okay? Now, without showing how they did any of this, this is what they got. And this time, they really combined things. They did this integration here at 4 minus this integration at 1 to give you this piece, minus this integration at 5, minus again the integration at 4, which they don't show you how they did it, or evaluation, not integration. I already did the integration. And that gave you this, and that gave you multiplied this by 3, numerator and denominator, and you get, skipping steps like crazy, 71.6, which was 11 point, whatever that thing might be, 11.8 or something like that, wasn't it? I've already gone off the slide. So you did go further because you went forward, then you went back, and your displacement was from here to here, but your total distance was that distance plus this distance. You move that over here. All right. Does that make sense?
They skipped a lot of steps. What do we indicate?
Say this point, yeah.
They skipped the step.
They skip steps like
Yeah,
that.
what do we indicate?
Okay, what we did, we evaluated that same integral we had. We evaluated it at 4 and made that positive, at 1 with negative, just like we had done with 5, the 1 was negative. Then we evaluated the same integral at 5, but with it being negative, and then we integrated it at 4 with the minus of minus, we made it plus, which basically doubled what this value was, minus 1, minus 5. And that's how we got it. Yeah. Yeah. The reason it doubled at 4, you had it in the upper value here, and then minus a minus down there, which is another plus. And it's the same expression that you're evaluating. Okay. And I was just being plumb lazy when I was writing it, because there's so much to write. All right. Any questions on that? And any questions? That was the last slide in the section. Okay? Homework exercises, I've given most of these before, but just to review, do either 5 or 7, they're both at Calc Chat. Do any of the odds 9 through 35, they're all at Calc Chat, 19's at Calc View. Do either 37 or 39, they're both at Calc Chat, 37's at Calc View. Do any of the odds 41 to 45, they're all at Calc Chat, 43's at Calc View. Any of the odds 47 to 51, they're all at Calc Chat, 47's at Calc View. Any of the odds 53 to 57, they're all at Calc Chat, 53's at Calc View. And then either 59 or 61, they're both at Calc Chat. And 61, by the way, is Buffin's needle experiment, which may give you a potential paper topic if you figure out who in the world Buffin was, or how he did this experiment, or what difference it made, or who uses it, or whatever. You might find the paper topic there. Do 63 is both at Calc Chat and Calc View. 65 is both at Calc Chat and, no, it's only at Calc Chat. And 67 is only at Calc Chat. Then do any of the odds 69 to 73, they're all at Calc Chat. 71's at Calc View. 75 to 79, they're all at Calc Chat. 75 is at Calc View. 81 to 85, they're all at Calc Chat. And any of the odds 87 through 91, they're all at Calc Chat. Any of the odds 93 to 97, they're all at Calc Chat. 93 is at Calc View. And you can explore doing 199 or 101. They should both be at Calc Chat. 103 is a particle motion problem. It should be at Calc Chat. Now, I kind of don't care too much for 105 and 107 because they got something, and they tell you, they put a big red X. This is wrong. Find describe why the statement's incorrect. I hate for you to work on something that's wrong, but that may be instructive, so they should both be at Calc Chat. True false, 109 should be at Calc Chat. 111 and or 113 should be at Calc Chat. 115 is one of those Putnam exam challenges if you are interested in doing that. And the section project is demonstrating the fundamental theorem if you are interested in that. So let's move on to 4.5. Okay. That took way too long to do that section. Okay. It was a whole section, but it was that part. It was basically one example. All right, let's start the slideshow again at the current slide. And we're still in Chapter 4, the last section in Chapter 4, integration, and 4.5 is integration by substitution. Okay. Now, to me, this is almost the beginning of Cal 2. Okay. Cal 2 starts with sort of more applications, but then it gets into techniques. To me, substitution is a technique of integration. They count it just another method of integration. So just think of this as what you're going to start next term, wherever you start that, wherever you are, that will be it. So 4.5 is integration by substitution. Now they start with this pattern recognition, which is okay, but I find it tedious to do that and then do it an easier way. Why don't we just do it the easy way first? But anyway, we'll do it. I'll do it first. We use a change of variable. That's the way to go. It's so much, to me, clearer. But some of you might like pattern recognition. We'll talk about the general power rule for integration to find an indefinite integral, which is basically a substitution. We'll use a change of variables, which is basically what we're doing here too. Not much difference here, is it? This is to find an indefinite integral. This is to evaluate a definite integral. Not a big change there. Though there is a subtle change, which is pretty nice. And then evaluate a definite integral involving an even or odd function. And that gives us another quick little thing to do. So let's first do pattern recognition. To me, again, I don't care for this, but if you like it, we'll go over it. In this section, you'll study techniques for integrating composite functions. I don't know if you remember back in pre-calculus, you got into composite functions, a composition between f and g, and you had to do all sorts of things with it. We've done a little bit of other stuff with it. This is why you did it all. You did it for chain rule purposes with taking a derivative. Now we're basically undoing that with integration. Okay? Integrating a composite function. The discussion is split into two parts. Pattern recognition, which frankly to me is all incorporated in change of variables, so why do it twice? But both techniques involve a U substitution. Okay? And my Cal 2 class, the gal who sits right here, she doesn't just say substitution, she says U substitution all the time. And I've gotten used to it now, but at first I didn't know what she was saying. With pattern recognition, you perform the substitution mentally. Well, why not just write it down? You're going to have to do it later to do it. And with a change of variables, you write down the substitution steps. It's so much easier just to write them down. The role of substitution and integration is comparable to the role of the chain rule in differentiation. You're just undoing it. Okay? You're undoing the chain rule. Okay? So, if you think back for differentiable functions, if y is some capital F function of u, and u, though, is a function of x, here it happens to be a little g of x, the chain rule states that d by dx of this f of g of x, okay, remember how that went? Took derivative of the outer function, evaluated at the inner function, then times the derivative of the inner function. That's the chain rule, remember? We love it. One of our favorites of all time. Now, from the definition of the antiderivative, it follows that if you had something here that was a antiderivative evaluated somewhere with, a derivative of something evaluated somewhere with that derivative of the something in here outside there, then you could just go directly from here to there and do your plus c if this is a antiderivative indefinite interval. Okay? If you see this, fine. Go for it. If you don't see it, it's real easy to do a substitution. So those results are summarized in this theorem, antidifferentiation of a composite function. Let little g be a function whose range is some interval I, okay, and let little f be a function that is continuous on that interval I. If g is differentiable on its domain, this interval I, and capital F, which is the antiderivative of little f, okay, on I, then if you're integrating f evaluated at g, and you happen to see this thing that's on the inside here has a derivative on the outside here, then you can just say, well, this will just be the antiderivative of the outer function evaluated at g. Okay? And because it's indefinite interval, you have to put a plus c. Okay? Now, you can write that down, or you can do it this way. Let u equal the g of x, the innermost part here. Then take du, and you see that g prime of x dx, and then just rewrite that as the antiderivative of f of u, okay, du, and that's capital F u du plus c. But then what we usually have to do is go back and get this u back into x's again. But you see how to get that? Just put, instead of u, put your g of x again. Okay? And you have a plus c because it's an indefinite integral. A lot of blah, 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 right? Let's actually, okay. Example 1 shows how to apply this theorem directly by recognizing first the f of g of x and the g prime of x. Okay? Note that the composite function in the integrand has an outside function f, inside function g. Moreover, the derivative g prime is present as a factor in the integrand. Okay? So they're saying the same thing over again. Your integral consists of some outside function f, outer function f, evaluated at an inner function g, but you happen to notice that the derivative of that inner function is also multiplied there and by dx, so you can just go directly to the antiderivative of the outer function. You've got it knocked. Okay? That's a lot to see and digest and keep straight. So much easier to do a u substitution. So much easier. And it keeps you straight. Okay? So here's example 1. Now, rather than pattern recognition, let's just start off and what we look for. Okay? Here's what we've got. We've got an integral of the function times something else under dx. Okay? Well, here's what you look for. Here is an inner function, there's an outer function. The squaring function is the outer function. And what you happen to note, the derivative of the inner function is right there. So what we do is say, let's take that inner function the innermost part of the most complicated part of the problem. Okay? Innermost part of the most complicated part of the problem, that's that. And you just write down, and it's so simple. Okay, let me get my pen back. Okay, let u equal x squared plus 1. The innermost part of the most complicated part of the problem. Okay? There's where you start. It's called a u substitution. And always the next step is then du is equal to what? 2x, but you're writing it in differential form, so that would be dx, right? D's always have d's, okay? You always have to have a d with a d, okay? All right. Now, what we do next is rewrite this. Our integral will now be, the innermost part here is u squared, and the outermost part here is right there. I'm sorry, the part here is du. Okay. Now that's an integral I think even I can do. What would that be? Anybody? All right. We're in chapter 4 still, integration. We've moved to 4.5, which is integration by substitution, and we're doing example 1 on the top of page 297. Okay? And we got down this far. Can anyone do that integration? Please say yes. You better. What is it? Pretty simple. What is it? We're just doing a lot harder than this on the last example. It's the antiderivative of u squared du. U to the third over 3, because it's indefinite, plus c. But this is our new variable. Let's go back to the old variable. U is, or u are, x squared plus 1. So it'd be x squared plus 1 cubed over 3 plus c. Now there's several ways you could write that. If you preferred, you could do 1/3 of x squared plus 1 cubed plus c. Or however, it doesn't matter how you finish it off, okay? And I think they do leave it in that form. It's pretty straightforward, isn't it? The key is finding the innermost part of the most complicated part of the problem. Let that be your u, then do your du, and then go to town with that. Okay, there may be some trial and error involved. You may find out, oh, that one doesn't really work that well. Try something else then. But this worked perfectly that way. Everybody got it? All right, to erase? Yay? Okay. Now let's see how they do it. By letting the g of x be the innermost part of the most complicated part of the problem. The most complicated part is the squaring part, okay? And the innermost part of that is the x squared plus 1, okay? So let that be your g of x, then your g prime of x. Only why call it g of x? Why not call it u, okay? That's what we're going to call it later, so why not call it that? Then u prime, or g prime of x, is 2x dx. I wish they had the dx in there. So now what we've got is your f, which they don't ever tell you what f is. That's the squaring function of g. That's the innermost part of that. That would be this. So without saying f was this, they immediately assumed you knew what that was. Again, that's making an unnecessary assumption. Just start here, call that u, that's du, and then do the calculus. It's just this thing of recognition, it may be fun and valuable, but it's just so much easier to let the you do your work for you. Okay? From this, you can recognize that the enneagram follows that pattern. It's so much easier to just do a U substitution and let the pattern take care of itself. Okay? In my mind. Okay? If you prefer seeing patterns, see patterns. Okay? If any of your seamstresses, you probably use patterns all the time. Okay? To me, this is a more difficult way. They make it seem like this is the easy way to do it. To me, this is more difficult. It's more involved and more you have to remember and think back and stuff. Just let the you do the work for you. All right, to erase. Move on. Using the power rule for integration. And again, if they had just put a U in there, it makes so much more sense. It's so much easier to see. Okay? It says, tries using the chain rule to check the result. And that is the answer, by the way. And when you do that, you'll find out you get exactly the original integral. Okay? Now, the integrand in that example fits the pattern exactly. You only had to recognize the pattern. You can extend this technique considerably with the constant multiple rule. Okay? Pulling out the constant multiple and then seeing if you do it. Many integrams contain the essential part, the variable part of g prime of x, but are missing a constant multiple. So then you just have to put one back in. In such cases, you can multiply and divide by the necessary constant multiple as shown in example 3. Well, guess what? They just skipped example 2. So let's go back and do example 2, because they go to 3. So let's go to 2. Find this, the integral of 5 cosine 5x dx. Okay? Now, if you can look at that and see that it's just exactly a pattern, that's fine. But if you don't want to stress your mind doing that, say, well, here's a function, an outer function. There's an inner function. Let's let the u be the inner function. Okay? So let's just do that. Let u equal 5x. And what's always the next step? Then du is equal to 5 dx. Perfect. Now, looky here. There's your 5 dx, this is your du, and this is cosine of u, right? So this becomes the integral of cosine u du. Now, I think even I can do that one. What is the antiderivative of cosine u du? Sine u. Okay? But what else? Plus c. Okay. All right. Now plug in what u was. U is 5x. So this is equal to sine of 5x plus c. And if you want to, take a derivative of it. Derivative of sine of 5x is cosine of 5x times chain rule 5. 5 cosine 5x. Derivative of c is 0. So you got exactly what you had there. That making sense? Yay or nay? All right? All right. Let's try example 3 then, if y'all are okay with it. All right, here's this one. Now, again, I say look for the innermost part of the most complicated part of the problem. What's the innermost part? X squared plus 1. Let that be your u. Let u equal x squared plus 1. And what's always the next step? Then du, for some reason this pen does such strange things. Okay, du is equal to 2x dx. All right, but up here we don't have a 2x dx. Now, I'll do it the way the book does it, or I'll do it the way I like to do it. I mean, either way, it works out being the same. In order for you to have a 2x dx up here, you have to multiply by 2, but if you multiply by 2, you also divide by 2, right? Otherwise, you're changing the problem, right? So divide on the outside, multiply on the inside. So this will be 1/2 the integral of, I'm just going to rewrite it to, the x squared plus 2 is u squared, and then we had, if you put the 1/2 on the outside, the 2 on the inside, you'd have a 2x here and a 1/2 here, and the 2x dx is going to be your du, and there you have it. Okay, the 2x dx is what you need on the inside, because you only have an x dx here. Multiply this by 2, but divide by 2 on the outside. You're multiplying by 1, which is fine to do. So this gives you 1/2 u squared du. Right? The du is 2x dx. There's your x dx. That's why I wrote those together. To make it 2x dx, multiply by 2, divide by 2. Divide by 2 on the outside, multiply on the inside. Now what you have is u squared du, but with a 1/2 on the outside. Okay? And what's the antiderivative of u squared du? Pretty easy, isn't it? U cubed over 3. One other little thing, plus c. Okay, now, here's an issue, okay? Do the integral first and then do the plus c. So this will be 1/6 u, oh wait, what is u though? It's your x squared plus 1. X squared plus 1 plus c. Okay. Now if you have any doubt about it, just take the derivative of this. Oh, yeah. But that's cubed. I was going to say, where's my cube? Because you see there's u cubed. Okay. So take the, say again? Okay. It's 1/2 times 1/3. It's 1/6. Okay. And if you were to take a derivative of it, 3 times 1/6 is 1/2 times x squared plus 1 squared times chain rule 2x. The 2 cancels out with the left 1/2 that was left, and you just had x. How's that? Okay. Yeah. Exactly the same answer. See how this works? No? Do you need to see another one before we move into change of variables for indefinite integrals? That's really still the same thing, I think. Yeah, I mean, we're doing the same thing. So let's see how they do it, okay? Forgot that this is one they've done. Any questions on mine before I erase it? Okay. So what do they do? This is similar to the integral given in example 1, except that the integrand is missing a factor of 2. Okay? So what do we do? Recognizing that 2x is the derivative of your innermost part. In order to get the 2x, they go to all the length of saying, to get this x here. So see what they've done? They moved the x over with the dx. And they left this part alone. So this part is your u squared. Okay. This part is your du, but you didn't have but an x dx, so you multiply by 2 and divide it by 2. This 1/2 you're going to pull outside and then leave the others on the inside. Okay? So that's what they're doing. To me, it's almost too much maneuvering around and it gets too confusing. But if you like doing it that way, do it that way. It's perfectly correct. Okay, so now you have your 1/2 on the outside. You have, this is your u squared, and this is your du. Okay? They like to say f of g of x than g prime of x. U is so much easier than g of x, and u prime is so much easier, du is so much easier than g of x. But if you like it this way, go it this way. Okay? So that will be then your u cubed over 3. Okay? Where u is your x squared plus 1. Okay. Now, the 1/2 times the 1/3, that's what gives you the 1/6. And then this part cubed plus 6. Same answer. They just didn't say u, they said g of x. To me, u is simpler. But if you like g of x, go this way. It's perfectly fine. All right. Now, what we've been doing is called the change of variable, a u substitution. So now they're going to go into that, which is the same thing we've been doing. With a formal change of variables, you can completely rewrite the integral in terms of u and du, exactly like I did, or any other convenient variable. If it was already a u, make it a v, or any other variable. Although this procedure can involve more written steps than the pattern recognition, in examples 1 and 3, it's useful for complicated integrals. You're going to have to do it for complicated integrals anyway, and to me it's simpler than f of x and g of x, but that's up to you. The change of variable technique uses the Leibniz notation for the differential, not the derivative, but the differential. That is, if u is equal to g of x being the innermost part, let u be the innermost part, then du is your g prime of x dx, which I don't even write it that way, I just take the derivative of whatever g was. And the integral in theorem 413 takes the form of the integral of f of u du. That's exactly what you got here. That's so much easier to me. That's so much easier to deal with than that. But that may be me, okay? The antiderivative of this is just your capital F of u plus c, and then go back and plug in what your u was, which is your g of x. It's pretty straightforward. So let's do one. Okay? Now, in this one, what seems to be the innermost function? So let's let u be that. 2x minus 1. Okay? What's always the next step? Second? du is equal to? Second? I don't think so. If u is 2x plus 1 minus 1, what is du? Is what? 2 dx, right? Write it in differential form. 2 dx. Isn't that true? Derivative of u is du. Derivative of 2x is 2 times dx. Right? Done. Right? Now, the other thing about this problem is I don't ever like to integrate. We just went past our break time. You need to take a break, anybody? I know I could use one. Do you want to finish this problem or come back and finish it, okay? I don't like to take an integral of a radical. How do I like to rewrite it? And hopefully you like to too. That would be the 2x minus 1 to the 1/2 dx. Exactly. Now, that is better. Should have done that first and then put my u over here. But now this will be what? The integral of? No, don't do that anymore. Plug it in, plug it in. U to the 1/2 du. Except we don't quite have a du. Du is 2 dx. We don't have a dx here. So you can either write a dx, a 2 there, and do a 1/2 out front. So that would be with that. Okay, I should have done that first too. Right? Because your du is 2 dx, so you need a 2 in there to pull a 1/2 out front, put a 2 in there, now you have the same. So, that would be 1/2. What's the antiderivative of u to the 1/2 du? U to the what? To the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Perfect. Now, looky there. The 2's go out again. Oh, and you also have a plus c. So what we have now is u to the 3/2 power, or 1/3 u to the 3/2 plus c. But because we got u's there, I want to go back to our x, so this will be 1/3 to the of 2x minus 1 to the 3/2 power plus c. Now that to me is a perfectly good answer. Yes? What did I do to the du?
Okay, so you have 1/2 the integral of u to the 1/2 power times du.
I'm not exactly sure where you are, but if you take this and just move it down here, okay? U is, or you are, 2x minus 1, and the du is 2 dx. Well, we didn't have a 2 dx. We only had a dx here, right? So I put a 2 in here and put a 1/2 out front, right? Okay. So now what I have is 1/2, the integral of u to the 1/2 du, right? So that's where it winds up. Okay. Now, I'm doing the antiderivative of this. Well, the 1/2's out front, okay? Antiderivative of u to the 1/2 du is, if you're taking the antiderivative of it, your du goes away, right? That's what you're doing. You're undoing your differentiation with your integral, okay? So that gives you u to the 3/2, and then multiplied by 2/3, or divided by 3/2. Whichever you want to do. And as soon as you do that, you see, when you lose the integral, you lose the du too. They undo each other, right? Okay? And then you have your plus c because of indefinite integral. And then the 2 goes into 2 there, and you're left with 1/3 u to the 3/2 power plus c. And then put in what u is, 2x minus 1 to the 3/2 power. And that to me is a perfectly good answer. If you wanted to, and I hope you don't, but if you wanted to, you could write that as 1/3 of the square root of 2x minus 1 cubed plus c, or you could have written it as 1/3 of the square root of 2x minus 1 cubed plus c. But why go back and put it back in a radical, leave it in the 3/2 power? That's exactly what the book did. Okay? And let's show it. All right, to erase this. Anyone still writing? Okay. Can I erase? Okay. First, let u be the inner function, 2x minus 1. That's what we did. Then calculate the differential. Du is equal to 2 dx. Okay? Just like we did. Okay? Now, using the fact that the square root of 2x minus 1 is the square root of u, dx is du over 2. Actually, that's how I like to do it, but they've quit doing what they were doing before. I don't know why. But why hang around with the radicals? Go on and write that as the 1/2 power. If they had written this as the 1/2 power, that would have been perfect. And now they wrote it to the 1/2 power. 1/2 the integral of u to the 1/2 du. When you take that integral, it's 1/2 of u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3, plus c. You have to have the plus c because it's indefinite. And that would be 1/3 u to the 3/2 power plus c, because, and again, they skip steps here, but if you'd written that as 2/3, then you can see why the 2's cancel out, divide away. And then you go back and plug in what u is, which is 2x minus 1. So it's 1/3, 2x minus 1 to the 3/2 power plus c. Perfectly good answer. No reason to go back and put it in radical notation. But you could if you wanted to. Okay. Now, any questions? All right for break? Okay. So I'm going back up to here. Pause this. We're going to come back and do example 5 first, and then we'll do that table that just, no, we'll do 5 and 6, and then we'll do the guidelines. Okay? I was just mentioning that all your tests that have been turned in by last week have all been graded, and your papers that were turned in by last week, which aren't that many, folks. Just got one more in today. That makes 3 for my biggest class of the term. 3, and we've only got 2 more days of class after today, so please get your papers in, and so I can get those graded. But I've graded test 2 and 3, but there's one person who hasn't turned in test 2 and several people who haven't turned in test 3, but you can always see your score. Okay. Now, any questions? Okay. Let's do example 5 and 6. They don't show this in the slide set. Now, example 5 is also available at larsoncalculus.com. You can see an interactive version of this type of an example. So here we have, now this one's admittedly a little bit trickier. Okay? So let's see how we can do this. Here's our integral. The integral of x times the square root of 2x minus 1, that almost looks familiar, doesn't it? Times dx. Okay. All right. And I did check, there's one person who hasn't turned in test 2. So you can always see your score. But I can't return them to you until I get that last one in. There were 2, there's still 2, but one of them withdrew, so that other person hasn't withdrawn yet. I don't know if it's going to or not, but that's why I haven't returned them yet. So you were asking. All right. Now, before I do anything else, what would be the first thing you do to that problem? Do what? Okay, and how would you do that? 2x minus 1 to the 1/2 power dx. Perfect, I like it. Okay, now what? Find u. Okay, let u equal what? 2x minus 1. Okay, then always follow that by then. Du is equal to 2. Say again? dx, right? Yay or nay? Okay, got it. All right, Houston, we do have a problem here, don't we? We have an x here that we can't put with the u, and we can't put with the du. Okay? Oh no, are we dead in the water? Not quite. Let's take this statement here and expand it. Let's solve for x. So what we'll do is add 1 to both sides. That would give you u plus 1 is equal to 2x. That's legal in most states, right? Yay or nay? Okay, and then divide by 2. So x is equal to u plus 1 over 2. All right. Now, we got some other issues too, and I'm going back and do it the way I like. They're changing the way they do it too. Here we only have a du, we don't have a 2du. So let's solve this and just make it a dx. Let's divide both sides by 2. Okay. Now I think I'm finally ready to rewrite my integral. So I'm going to put my integral down. This x is, now I'm going to pull out the 1/2 here. So put a 1/2 out here. And then the x becomes a u plus 1. And my parenthetical expression is u to the 1/2, right? And then we have our dx is du over 2, so there's the du, and we have another 2 out front, okay? So that's going to be a 1/4. So what we've got now is 1/4 the integral of u plus 1 times u to the 1/2 du. All right. Now, that's 1/4. That 1/4 stays 1/4. And we're going to still have our integral here. But let's distribute the u to the 1/2 across the parentheses, right? So what will this one be? U, that's to the first power, which would be u to the 2/2 times u to the 1/2 would be u to the 3/2 plus 1 times u to the 1/2 is u to the 1/2 du. Okay, I think I'm ready to integrate now. Be 1/4. What's the antiderivative of u to the 3/2? U to the what? 5/2, up by 1, which is 2/2. That'd be u to the 5/2, but it also has to have a yeah, 5/2 in the denominator, or you could write that as 2/5. I like to write it that way. Plus antiderivative of u to the 1/2, u to the 3/2. Is that what I heard? Times what? 2/3. Okay, and plus c. Okay. So let's combine what we've got. Well, notice we have a 2 in both numerators here, and let's do 2 into this one and make that a 2. So what we have is 1/2 of, and let's go on and plug in what u is, 2x minus 1, 2x minus 1 to the 5/2 over 5 plus 2x minus 1 to the 3/2 over 3 plus c. Now, when it comes to denominators, this book likes to just come up with all kinds of creative ways of writing them. And if you're doing this on Enhanced Web Assign, if you don't guess the same way they're doing it, they'll tell you it's the wrong answer. And I sort of hate that, but what you could do, least denominator, the denominator between these two is 15. So you could do a 3 here and a 5 there, and you could do it that way. To me, this is a perfectly good answer, just like this. But since you have the 1/2 out here, if you wanted to do that, here is another answer, but it's nothing any better about it. 1 over 30, that's your 15 from there, and your 1/2 from there. And then this would be 3 times 2x minus 1 to the 5/2 power plus 5 times 2x minus 1 to the 3/2 power plus c. Okay. there's nothing any better about that. I don't know if that, no, that's not how they leave it either. Okay. They multiply the 1/2 in and make it this thing over 10 and this thing over 6. Fine, that's just as good of an answer. Okay. So they wrote it as 2x minus 1 to the 5/2 power over 10 plus 2x minus 1 to the 3/2 power over 6 plus c. Another perfectly good answer. None of these is any better than the other. This is just as good as the other two. That's okay. That's all right. Okay. They actually write the 1/10 in front. It doesn't matter. Okay. Any questions on that? A little bit trickier here because you couldn't incorporate this x into your dx, but you can solve for x here and do it, and then at this step you can distribute and you still have a very reasonable answer. All right. So there was example 5. Any questions on that? I want to move on to 6. Okay. Let me erase what we've got here if no one needs it any longer, do you? Anyone need it? Okay. And let's do example 6. Find this one. Integral of sine squared 3x cosine 3x dx. All right. Now, there's a little bitty part of me that would say maybe your recognition thing might be helpful here. But there's another part that says that's not necessary anyway. There's another part that says you can actually do 2 substitutions here if you want to. Which way would you like to go? What would you do with a problem like that? Say again? Still can't hear.
I'll go for what's in the middle.
Okay. So tell me your first step.
Find the U.
Okay. I like it. What would be your u?
I'll say 3x.
Let u equal what?
3x.
Okay. All right. That's a good way to go. What we're actually doing here is we're going to wind up doing 2 substitutions. So there's your first one. Then du is equal to 3dx. Perfect. But we don't have 3dx. We have just a dx here. So let's divide both sides by 3. Okay. Now, let me write down what we have now. We have the integral of sine squared u, 3x is u, cosine u, and then we have a du over 3. So put the 1/3 out here. All right. Now, where would you go from there? Yes, except I wouldn't call it u. Make up some other variable name. Don't use u or x, something else. V, okay, let v equal what? Sine u, okay, then d what? V is equal to cosine u. You need one more thing. Du, not x. You're stuck with u's now, okay? Now, what we have here now is 1/3 the integral v is sine u, so that would be v squared dv. You see that? The dv is cosine u du, and this is v squared. Can we do that one? Please say yes. V cubed over V over 3, I think is what you said, right?
Yep.
Okay, I wrote a V instead. Okay. V cubed over 3.
Plus C.
Okay. Plus C. Perfect. So let's start plugging in. This will be 1/9 V cubed plus C. But V is what?
Sine U.
Sine U. So that'd be 1/9 sine cubed U plus C. But that would equal 1/9 sine cubed, and what's U? 3x plus C. There's our answer. We actually did 2 substitutions, one for the 3x, and then the next one for the sine, and sure enough, we got one that's supposed to be a 9. I don't know how it became a 2, okay? It's weird, okay, totally strange. Whoops, it's not erasing either. That's 1/9 sine cubed 3x plus C, okay? And then just for fun, if we want to take a derivative of this, 3 times 1/9 is 1/3 sine squared 3x times 3, which would be, derivative of 3x would be times 3. The 3 cancels out the other one. You have sine squared 3x. And then times cosine 3x, same rule. I forgot to do one. Okay? And that's exactly what we've got there. All right. Good deal. Any questions? See how that works. Let's make sure they got the answer right in the book. 1/9 sine cubed 3x plus C. Fantastic. All right, and they did the checking by differentiating too. Any questions? Can I move on? All right. All right, the steps used for integration by substitution are summarized in the following guidelines. Choose a substitution U is equal to G of X. I don't care about the G of X. Find the innermost part of your most complicated part of your problem. Let that be your U. And that will be some function of whatever your variable is. So let's just call it U. Usually it's best to choose the innermost part of your composite function, which is the most complicated part of your function, and use that quantity, such as a quantity raised to a power or whatever. Okay? Then you do, once you have your U, then do your DU. Okay? And I don't mess around with the G of X, just whatever that innermost part was, do the DU of that. Be sure you put a DX to correspond with the DU. You're writing it in differential form. Rewrite the integral in terms of the variable U. Fantastic. And then find the resulting integral in terms of U. Okay? In other words, you integrate with respect to U. Usually that's an easier thing to do now. Okay? Replace then the U by the G of X that you got to begin with. Okay? To obtain the antiderivative in terms of X, check your answer by differentiating. Now what they didn't say is, when you find the resulting integral in terms of U, put your plus C. Don't forget to do your plus C. Okay. Now, I think we're ready then for the next one, which is the general power rule for integration, which I don't know why they make a big deal about it, because it's what we were just doing. Okay? They're just giving it a new name. One of the most common used substitutions, which we've already been doing, involves quantities of the integrand raised to a power. And we did that on at least 2 of the 3 of the last several, okay? Because of the importance of this type of substitution, it's usually given a special name, the general power rule of it for integration. Why give it a new name? Just do the same thing we always have been doing. If G is the differentiable function of X, then if G of X is raised to some power n, now that n doesn't have to be an integer. It can be a rational expression. It can be anything. Then the g of x raised to the n times g prime of x is g of x raised to the n plus 1 over n plus 1. The very thing we've been doing, plus c. Now this only works for n's that are not equal to negative 1. Why could n not be negative 1? Anybody? The denominator would be 0. You can't ever do that. Okay? So equivalently, if u is equal to g of x, then the integral of u to the n, the u is u to the n plus 1 over n plus 1, as long as it's not negative 1, plus c. So much easier to do a u substitution here than a g of x substitution. I don't know. It just seems like extra things to write. Okay? So let's do one. Okay? Don't even bother with the fact you've got anything here. What would you say your substitution should be? Or how would you approach that? Say again? Anybody? Say again?
You said what?
How would you approach the problem? There's your integral. How would you do it?
Find the u.
Okay, what would be your u?
3x minus 1.
Excellent, excellent. Let u equal 3x minus 1. What's your next step? Then du is equal to 3 dx. Perfect. Okay? And look at here. There you got your 3, there you got your dx. That part right there is your du, and this will be u to the 4th power. So rewrite this as the integral of u to the 4th du. How do you integrate that? Say again? U to the 5th over 5 plus c. Now what you do? Go in and plug in what u is. That's 3x minus 1 to the 5th power over 5 plus c. Now they probably will write that. I don't know. They change it just about every time. 1/5 3x minus 1 to the 5th plus c. I don't know. How do they write it? Yep. No. Oh, okay. There are 5 parts to this one. I was looking at the last one. They left it in the first form I had. 3x minus 1 to the 5th over 5 plus c. Perfectly fine. Okay? Less. What's that? Okay. So let's erase this. And they started it here. That's u to the 4th du. That would be u to the 5th over 5. Without doing the u, they just did it. Okay. So here's the b. What would you do with that? Anybody? What would be your u?
X squared plus x.
Yes, the x squared plus x. That's the most complicated looking part. The other part looks a little simpler than that part, so that's going to be our u. Let u equal x squared plus x. And what's your next part then? du is equal to 2x plus 1 dx. Perfect. And looky there. This part right here is your du, and this is u. So your integral now becomes the integral of u du. That's it. And how does that integrate? u squared over 2 plus c. And then plugging back in, that would be x squared plus x, that's your u, squared over 2 plus c. That should be our answer. All right. X squared plus x squared over 2 plus c. Perfect. Okay. So they just go straight to it and say x squared plus x squared over 2 plus c. Excellent. Any questions?
Is there any more harder examples?
I'm sorry?
Is there any more harder examples?
Let's see if there are. Let's do the C part. Okay? What would you do with that? Second? What would be your U?
X cubed minus 2.
Second?
X cubed minus 2.
Perfect. There's your thing. You see, after a while, they get so easy. I'm sorry. I wish I could make them harder. So we're going to let U equal x cubed minus 2. Then, what's your next step? du is equal to?
X squared.
Oh, yeah, x squared. Okay, that's okay. X squared. Second? 3x squared dx. Perfect. And there's your 3x squared dx. That's your du part. And this would be the integral of u to the 1/2 du. And what would be the antiderivative of u to the 1/2? U to the 3/2 times 2/3 plus c. So that'd be 2/3, and then u to the 3/2, u is x cubed minus 2 to the 3/2 power plus c. Okay? 2/3 x cubed minus 2 to the 3/2 power plus c. Fantastic. Let's see how they did it. I'll erase this. Any questions before I erase it? X cubed minus 2 to the 3/2 power divided by 3/2 or times 2/3 plus c. And then they write it as 2/3 times x cubed minus 2 to the 3/2 power plus c. Good deal. Okay, that's the C part. Let's do the D part. What would you do with that? Say it.
You can rewrite it where the denominator, like, instead of it being,
Like, I don't like fractions. So
like,
Okay.
change it to -2 from the exponent.
Okay. All right. I like that idea. Okay. So that would be the integral of minus 4x times 1 minus 2x squared to the -2 dx. Okay. Then what would you do?
U is
Let u equal, and what would you say it was? 1 minus 2x squared. Then du is equal to minus 4x dx. Perfect. And there's your minus 4x dx right there. That's your du part. So your new integral will be,
1 minus,
second, do the integral first. U to the -2 du. And then integrate that, and what do you get? Negative. Say again. To the negative what? To the -1. Increase the exponent by 1, right? And you've already divided by -1 by that minus sign, right? You didn't realize you did that, but you did, right? And then, one last part, plus C. Okay? So this will be minus, I'm going to put it back in the denominator, U is S, 1 over 1 minus 2x. Second? Okay, good question. Okay? When you're doing this, integrating a power, you put the base here, okay? Increase this by 1. Minus 2 plus 1 is minus 1. Then divide by your new thing here. So you're dividing by minus 1, which is the same as multiplying by minus. Right? That's where it came from. Dividing by minus 1. Okay. Now you don't have to write it this way. I'm just saying you could. Plus C. Now let's see if that's how they do it. Yep, that's exactly how they leave it. Make sense? Yay or nay? Okay. So let me erase my ink and show how they did it. They just write it as 1 minus 2x squared to the minus 1 over minus 1. And then they do 1 over minus 1 is just a minus sign 1 over 1 minus 2x squared plus C. All right, their last one here. Okay, what would you do with that? Anybody? Nope. What's the most complicated part? The squared one. What's the innermost part of the squared one? Cosine. That's what you're squaring. Don't worry about that one. Okay? All right. So let U equal what? Not that hard. Cosine x. Then du is equal to negative sine x dx. Oh, they've been really nice to it before, but now we got a minus in there because derivative of cosine is negative sine. Yeah. What's that? Okay, I'm letting the innermost part of the square, see the most complicated part here is the squaring function. So the innermost part of that is the cosine. That's what you're squaring. So that's what I'm letting be u, okay? And then du is going to be derivative of cosine, which is minus sine x dx. Well, we have a sine x dx, we don't have a minus sign, so let's multiply or divide both sides of this by minus 1, which makes that be a minus du is equal to your sine dx, sine x dx. So now I'm going to rewrite that to be minus the integral. That minus comes from the inside. And then your cosine was your u, so that's u squared. And then the sine x dx is your minus du, but the minus is already out front, du. Okay? Now, what do I do with that? Antiderivative of u squared du. U cubed over 3. But the minus sign's out in front. Okay? What else? Plus c. Now plug in what u is, or u are, cosine x. So it's minus cosine cubed x over 3 plus c. Okay? And that is exactly what they get in the book. You see it? So I'm going to erase mine because I don't know where they're going to write theirs. I don't want it writing on top of it. There, they wrote it down there. Minus cosine x cubed over 3 plus c. All right. Any questions? All right. So that's our example 7. All 5 parts of example 7. Now, up to now, when we've been doing our substitution, which they also call a change of variable because you're letting u equal some variable of something else, usually x or something. We've been doing it only for indefinite integrals. Now we're going to do it for definite integrals. Now there are two ways to do this. I count one of them a little bit easier, though it has a little subtle change to it. The other one's maybe a little harder, but maybe more easily. It looks more like what we were just doing. So I'll let you decide which way you go, but I think you'll see which way I prefer fairly soon. When using u substitution with a definite integral, it is often, catch this, often convenient to determine the limits of integration for the variable u rather than converting the antiderivative back to x and evaluating at the original limits. It's just usually easier to change your limits to represent u rather than leaving them for x and having to go backwards and redo it. This change of variables is stated explicitly in this theorem, and this is how it goes. If the function u equals g of x has a continuous derivative on the closed interval a to b, and f is continuous in the range of g. So remember, f is a composite function. Okay, it's continuous on the range of g. Then the integral, the definite integral from a to b of f. Now remember, the a and the b are x variables, not the u variables, the x variables. Okay, but f is evaluated at some function of g. Okay, and then you have your g prime, which to me this is a messy way to write it. But then when you make the u substitution, let u equal g of x, then du would be g prime of x dx. This becomes, now here's what they're doing. Since you've changed your variable from x to u, change your limits from x equal a to x equals b to g of a and g of b. Now, when you write it all out, this makes more sense, okay? So don't get tied up with this yet. But this is what you become, and this looks more confusing than it is, but it actually is an easy way to go. So let's do this one, okay? What would be your first step? Anybody? Say again? Let u equal what? X squared plus 1. Then du is equal to 2x dx. Perfect. But we don't have a 2x dx. We have an x dx. So what we want to do is divide this by 2 and divide that by 2. Now we have an x dx. Okay? So now I'm going to rewrite my integral. I'm not going to write down my limits yet. I'm sorry? Okay, put 1/2 in front. Okay, I'll buy that. Say again? U cubed du. Very good. But I didn't write down my limits, and here's why. Because these limits, 0 and 1, stand for the x values. So in this statement right here, I'm going to put 0 in for x. And what do you get u to be? 1. So your lower limit here is going to be 1. And what would be the upper limit? When x is equal to 1, what's u? Say again? Yes, 2. Okay. That will become 2. Because 1 squared plus 1 is 2. Now we don't have to go back and substitute back in again. We'll just do it using u's. So what's the antiderivative of u to the third du? U to the fourth over 4, evaluated from 1 to 2, because those are your limits on U. So you can just plug those in here. So this will be now, that 1/4 isn't going to deal with anything, so let's pull that out too and make it 1/8, and we'll evaluate this. 2 to the 4th power is 16. Okay, we already pulled the 4 out. Minus, and 1 to the 4th power is 1. Okay, so this is going to be 1/8 of 15, which is 15/8. Okay. I was looking on the wrong page, and I said, no, they couldn't possibly get that answer. Okay? Yeah, 15/8. So much easier than doing it for U than going back and substitute back in X for U and then plugging in the X values. Not a lot easier, but it's easier. Okay. And that's usually the way to go. I'm sorry?
Why do we change 1 to 2 instead of 0 to 1?
Okay, here's what we did. These are our limits in X. So as soon as you make the U substitution here, make the U substitution here too. When X is equal to 0, 0 squared is 0 plus 1 is 1. U is equal to 1. When X is equal to 1, then 1 squared plus 1 is 2. U is equal to 2. Sometimes it'll be a lot more complicated than this, but this one is pretty straightforward. You just plug these values for your X's in here, giving you your U values for U's.
Okay, so I just subtract.
What is that? What?
That's negative 1/2.
Okay, that's not a negative one, that's equal 1/2.
Okay.
Yeah, I'm sorry. Okay, got it. Okay. I'm sorry, I didn't understand your question. All right, let's erase my scratch, and we'll see if they do it any differently. I'm guessing not much. To evaluate the integral, they did the same thing you did. First, identify what U should be. U equal X squared plus 1. Once you get what U is, figure out what du is. Du is 2x dx. We don't have a 2x dx. We have an x dx, so let's divide both sides by 2, and that gives you, well, they don't even show what they do next. But anyway, before substituting, determine the new upper and lower limits of integration using this. Your same substitution here will substitute in the x values here to get your new u values on the integration. So that would be when x was 0, u is 0 squared plus 1, which is 1. The upper limit when x was 1, u is 1 squared plus 1, which is 1 plus 1 is 2. So now it'll be going u from 1 to 2 rather than x going from 0 to 1. Okay? Now, doing several things at once here. This was our original when we did the du and found out you needed 1/2 dx. We did that. The 1/2 is out front now. Oh, I see. They're doing it their old way now. They're multiplying this by 2 and dividing by 2 out here, which is fine. It's perfectly fine. It'll be a little confusing, but it's still fine. Perfectly good. Okay, and these are the original limit, integration limits for x. So they left it in x so far. Now they're going to do their u. The 1/2 is still here. The limits change from 0 to 1 to 1 to 2. And this becomes a u cubed. And this thing becomes a du. The 1/2 is out front. Now we do that integration, which is 1/2 out front. This is u⁴ over 4, evaluated between those two limits. And when they do that, you get, okay, they left the 1/2 out front. They didn't pull out the 4 with it. You could have, we did, that was easier. But now, 2 to the 4th is 16, divided by 4 is 4. And 1 to the 4th is 1, divided by 4 is 1/4. And this will be 16 fourths minus 1/4 is 15 fourths. And half of that would be 15/8, which is what we got. To me, their algebra is more complicated, but it's still doable, still correct. All right. Any questions? Okay. How are we doing on time? We got a little more time. Now, notice that you obtain the same result when you rewrite the antiderivative of this. If I were doing this, I wouldn't have changed the variables here. Rewrite this back to x squared plus 1 raised to the 4th power of 1. In other words, you're substituting back in your u is x squared plus 1. Substitute back in 1/2 in front. This is the 4th over 4. And then plug in your x values of 0 to 1. And this would give you 1/2 of, you put a 1 in here, you get 1 squared, which is 1 plus 1 is 2, raised to the 4th is 16, over 4, which is 4, minus, when you put in the 0 here, that gives you 1 to the 4th, which is 1 over 4, which is 1/4. You get exactly the same answer. It's just you've had to do an extra step of going back and then going back again. You get the same answer, 15/8. Okay? Just which way you see best. To me, the first way seems easier, but I'm pretty lazy. All right. Now, before we get into integration of even and odd functions, let's do example 9. All right, I think this gives us the most room. Example 9. Evaluate this definite integral. The integral from 1 to 5 of x divided by the square root of 2x minus 1 dx. What would you do first? Second? You want to move it upstairs? Okay. And in exponential notation? Yes, I thought so. So this would be the integral. It's still in x's, so it's 1 to 5 of, okay, I'm going to write this one first. 2x minus 1 to the negative 1/2 times x dx. Because I just have a sneaking suspicion that x is going to wind up. But maybe I'm wrong, okay? All right, now what? Say again? Find u. And what would be the u? Where's u? Okay. Let u equal 2x minus 1. Then du is equal to, second, 2 dx. Okay. Hey, we got problems, Houston. Okay. First, we want the dx by itself, so let's divide by 2. So the du is going to be over 2, so next step, that'll be out front. Okay. But here we have the x again. Remember how we dealt with it before? Solve in this thing up here, and actually it looked like almost the same thing. What was that become then? Solve for x up here. U plus 1 over 2 equal x. Yeah, that's what you get. Okay? Now, let's start rewriting our integral then. So I'm going to put it like that. Okay, I'm not going to do the limits yet. We could if you wanted to. But let's start with, we got a 1/2 from here and a 1/2 from there. That's going to be a 1/4 out front. Okay? And now I'm wishing I had left the x in place. That would be a u plus 1. That was my x. And then the next part is u to the minus 1/2 power. Right? And then we have our du. But let's now change our limits. Okay? We use this right here. When x is equal to 1, what is u equal to?
X equal to 1, that's 1.
It's going to be, u's going to be 1 as well. Ooh, that's not bad. Okay? And when x is equal to 5 up here, what's u going to be? 9. Okay. So that will be going 1 to 9. Okay? Now, rewrite here 1/4 the integral from 1 to 9. Let's distribute. And what do we have there? U to... Okay, but we're going to distribute this across here and here. What does that give us? U to the 1/2 plus to the negative 1/2 times du, and that will be 1/4 times, what's the antiderivative of u to the, say again? Yeah, we will, but we're going to do it at the end. Let's go on and do the antiderivative of that. U to the 3/2 times 2/3 plus u to the 1/2 times 2. Okay? And then we'll evaluate that from 1 to 9. Okay? Say that one more time. The first one here.
Yeah, I know you put 2 over. Oh, no, you didn't. I was reading that.
Okay. Are we okay? All right. Now, before I do anything else, I notice we have a 2 in both numerators here, so let's wipe out that and make it just a 2 down there too, just to make it a little easier. Okay? Now, so this is going to be 1/2. Now let's plug in the u equal 9. I like to always take the square root first and then cube. Otherwise you get really big numbers. So let's do the square root of 9 is 3 cubed is 3 cubed is
3.
3 cubed is 3 times 3 times 3. 27 divided by 3 is 9. Okay, so the first part there is 9 plus, okay, and then it'll just be the square root of 9, 3. So we have 3. Now we're going to subtract off the denominator, and this is all inside the bracket there, so it's going to be a minus. When you put a 1 in here, the square root of 1 is, cubed is, divided by 3 is 1/3, so that's going to be a minus 1/3. And then we're going to plug in the 1 for here. The square root of 1 is minus 1. Okay, now that's going to be 1/2. Let's just do the whole numbers first. 9 plus 3 is 12, minus 1 is 11, minus 1/3. So that will be 33/3 minus 1/3 is 30/3. So it would be 1/2 of 30/3. Is that right?
No, it's
33/3 minus 1/3 is 32/3. Yeah. Okay. And the 2 will go into 32, 16. So I get 16/3. Oh my goodness, they did too. Good for them. All right. Does that make sense? All right. So that was our example 6. Oh, I'm sorry, example 9. Okay. Now, we've got just a few minutes left, right? So let's do integration of even and odd functions. Okay? Even with a change of variables, integration can, believe it or not, be difficult. Okay? Occasionally, you can simplify the evaluation of the definite integral over an integral over an interval that is symmetric about either the y-axis or about the origin by recognizing the integrand to be an even or an odd function. Okay? So if you are integrating a function that looked like this, what kind of function is that? What kind of function is this? Can you see? That would be the graph of it. What kind of function is it? Huh? That would be an even function. Now note if you're going from minus a to a, integrating this even function over that, how could you make that a little simpler? Because it's an even function, it's exactly the same on this side as it is on that side. So you could just do twice the value from 0 to a, right? And that would be this part plus that part. That would be twice this part, okay? Now, I don't know if you've noticed this or not, but when you're evaluating something that's at 0, it's usually really easy to evaluate. So it's a lot easier to evaluate 0 to a than minus a to a. Just double what you get from 0 to a. But what would happen here? What kind of function is this? Odd function. And if you evaluate from minus a to a, guess what? This and that wipe each other out. That answer is 0. Because this is a positive area, that's a negative area. Adds a 0. Okay? So use these to your advantage. Okay? Here's the theorem that states that. Do we have time for it? I think we do. 5 minutes. Integration of even and odd functions. Let f be integrable on a closed interval from minus a to a, exactly the same thing on one side as the other. If f is an even function, then this integral from minus a to a of f of x dx, if f is even, it's just twice the integral from 0 to a of f of x dx. That's usually just as easy to do the antiderivative and a lot easier to do your limits because 0 is so easy to plug in. But if f is an odd function, evaluated from minus a to a, don't even mess with it. That's just going to be 0. Because whatever it does on one side is opposite of the other side. You add those together, you get 0. Okay? That makes things very easy. So let's do one. Do we have time? 4 minutes. Okay? So let's do this one. Okay? Or you think not? It may take too long. So let's just hold there and we'll begin there next time. Example 10. Let me give you homework exercises because I knew you didn't want to run out of time for that. Okay, homework exercises do either 5 or 7. They're both at Calc Chat. 5's at Calc View. Do any of the odds, 9 to 29. They're all at Calc Chat. 15's at Calc View. Do either 31 or 33. They're both at Calc Chat. 31's at Calc View. Do 35. It's a Calc Chat. 37 is a Calc Chat. Any of the odds, 39 to 47, they're all at Calc Chat. 45 is a Calc View. Do any of the odds, either 49 or 51, they're both at Calc Chat. 49 is a Calc View. Any of the odds, 53 to 59, they're all at Calc Chat. 53 is a Calc View. Any of the odds, 61 through 67, they're all at Calc Chat. 65 is a Calc View. Any of the either 69 or 71, they're both at Calc Chat. 69 is a Calc View. And then we'll hold off and do the rest of those next time. Okay? Good deal. Any questions? And that finishes, when we finish this last example, that will finish chapter 4. So what we'll do then is next time move right into chapter 5 and we'll do 5.1. I think we'll have time to do 5.2. We may or may not mess with 5.3. We'll just play it by ear and get as much done as we can. Good deal. Thank you.
Chapter 2.
You need to see it or get it?
See.
See it, okay. Let me end this so it can be